Today we present WIPES, a novel wavelet-based primitive designed to bridge this gap. This is a joint work between Nanjing University and Tencent, presented at ICCV 2025. Let's start by framing the problem. The current landscape is dominated by two paradigms. On one hand, implicit neural representations, or INRs, offer great expressive power but are plagued by spectral bias, which limits their ability to capture high-frequency details. More critically, they introduce a significant computational bottleneck during training and inference. On the other hand, explicit methods like 3D Gaussian splatting have achieved real-time rendering, but this speed comes at a cost. Their reliance on Gaussian kernels, which are inherently low-pass filters, imposes a fundamental limitation on reconstruction quality. This low-pass nature of Gaussians is not just a theoretical issue, it has profound practical consequences. To model sharp edges or intricate textures, one is forced to overcompensate by using an enormous number of tiny Gaussians, leading to bloated models and inefficiency. Our quantitative analysis confirms this. On the Kodak benchmark, WIPES achieves a significant PSNR gain of over 5 dB, with an identical primitive count. The visual evidence here is stark. The Gaussian representation completely fails on the complex rooftop textures, whereas our method reconstructs them with high fidelity. So, how do we overcome this? Our solution is to redesign the primitive itself. We introduce WIPES by augmenting the standard Gaussian with a cosine modulation term. The key insight here is the learnable frequency vector, f, which allows each primitive to adaptively shift its energy across the frequency spectrum. This empowers our representation to model not just low-frequency content, but any arbitrary frequency band. Crucially, and this is key for performance, our formulation retains a closed-form analytical solution for volumetric integration, allowing us to leverage the speed of forward splatting without modification. The integration of WIPES is straightforward. We initialize from a point cloud and substitute the standard Gaussians with our more expressive wavelet primitives. A core component of our framework is a custom-built, differentiable wavelet rasterizer that handles the projection and blending efficiently. The pipeline is highly generalizable. By integrating a deformation field, for instance, we can seamlessly extend our method to dynamic scenes, positioning WIPES as a truly universal primitive for a spectrum of vision tasks. This slide provides a compelling demonstration of WIPES's core advantage. When tasked with representing these high-frequency Moore patterns, the Gaussian-based approach exhibits a clear modeling failure. Its low-pass bias makes it impossible to represent these signals correctly. In contrast, WIPES primitives learn the appropriate local frequencies, resulting in a near-perfect reconstruction. This isn't just an incremental improvement. It's a fundamental solution to the spectral limitations of prior explicit methods. For our first set of experiments, we looked at 2D image fitting. As the visual comparisons suggest, our wavelet-based primitives are quite effective at capturing fine details. For example, you can notice the improved clarity in the architectural textures and the sharpness of the statue's features. This qualitative improvement is supported by strong quantitative results on standard benchmarks. Importantly, these quality gains are achieved while maintaining a highly efficient rendering speed, demonstrating a favorable balance between detail and performance. Next, we applied WIPES to the more challenging task of 5D novel view synthesis. Here, the goal is to reconstruct complex 3D scenes. Our approach shows a notable capability in handling traditionally difficult elements. For instance, in the error maps and detail views, you can see how our method better preserves high-frequency textures in the painting and foliage. It also appears to more faithfully reconstruct challenging specular reflections, like those on the car's body and the mirror frame, which can be problematic for other methods. To test the versatility of our primitive, we extended it to 6D dynamic novel view synthesis by incorporating a deformation field. The idea is that a more expressive primitive might allow the network to better model complex motion. The results appear to support this. Visually, our approach yields sharp details on moving subjects and produces stable reconstructions of dynamic elements, like the fabric on the character's clothing. This suggests that the frequency adaptability of wipes is also beneficial for representing scenes that change over time. To conclude, we've presented wipes, a wavelet-based primitive designed to address the spectral limitations of Gaussian representations while maintaining rendering efficiency. We've demonstrated its versatility across a range of tasks, from 2D image fitting to dynamic 6D scene reconstruction. We hope this work offers a promising direction for developing more expressive and flexible primitives for visual representation. Thank you for your time.